Okay. And as a quick reminder, if you have a question, you can post it either in chat or Q&A, raise your hand, something like that. And Dr. Rahman says that she will answer it immediately if it's something that's a clarification, or if it's a more of a follow-on, she'll save it till the last part of the presentation. All right. And I guess with that, please take it away, Dr. Rahman.
All right, thank you. Hi, everybody, and thanks so much for coming. I'm Diana Roman. I'm a volcanologist at the Carnegie Institution for Washington, it's Carnegie Institution for Science here in Washington, D.C. And I'm going to tell you a little bit today about our evidence, basically documenting a newly discovered large volcanic system in Alaska. So as mentioned, I'll try to keep an eye on the Q&A. So if I see a quick clarification, I'll try to answer it, but otherwise I'll do the questions at the end. I'm going to try to leave about 10 minutes for questions, and we can talk about this study or about questions about volcanoes in general. So before I leave my title slide here, I just want to make a couple of points about my field, volcanology. The first is this huge list of co-authors. So this is a very big and multidisciplinary team that's really contributed to this, this finding. And we all have very different subdisciplines. So we're all volcanologists, but we come at our study of volcanoes from very different perspectives. So for example, I'm a seismologist. I look at tiny earthquakes that happen beneath volcanoes to understand them. But I have other colleagues who look at gas that comes out of volcanoes, the way the volcano deforms, the deposits it leaves in the geologic record, and so on. So it's been a really great opportunity to work with many different people, and this is kind of an ideal and we hope a typical way to work on volcanoes. The other point I want to make is this is really a story of discovery, and one of the interesting things about natural hazards focused fields like volcanology or earthquake science, even things like pandemics and economic events, is that we can't, really set up the experiment. We can't do, here's our hypothesis, and okay, you volcano over there, we want you to do this now while we've got you instrumented. We kind of just have to react to what the planet gives us. So this is a very typical study in volcanology, in that we went out to do this work with a very different aim, and really weren't expecting to figure out that there was this large caldera there. So it's kind of a different mode of working in science, and it's quite fun because you always come away with something interesting, and it's often very surprising. All right, so I'm going to talk about the system that we found, which is in the Islands of Four Mountains in the Aleutian Arc, Alaska, and I'm just going to start by giving you a little bit of orientation as to where we are. So up on the top here, I've just got a map of Alaska. So Anchorage is over here on the Alaskan mainland. And the area I'm going to be talking about is in this little set of islands out here in the middle of the Aleutian Arc, which is what we call this big chain of volcanoes. I'll get to how it formed in a minute. So the main point is it's very, very remote. There are a few villages out here, but it's basically uninhabited, and it's also very difficult to reach. So when we went out there for the work we did that is the basis for this study, we were out there for about 3 weeks in 2015, and then we came back in 2016 in the summer. And the way we get out there is actually on a boat. So you can see a picture down here of our boat, the Maritime Maid. And we live on the boat. The boat also carries our helicopter, which is over on the left, and that's what we use to get from the boat to the island and back every day. And it's a really fascinating mode of working. I actually had a lot of fun. You sort of get into this mindset very quickly of, this is my life. I wake up in the morning and the boat cook has made me breakfast, and then I commute to my job, and Dan, the helicopter pilot, flies me to my job, and my job is to dig holes in the volcano. And then at the end of the day, I fly home and they feed me dinner. And it's very strange to come back to civilization after that, and people want money for things, and you have to kind of reintegrate from this very simple and strange lifestyle that you've gotten habituated to. But even then, there's strange things that happen every morning. You wake up in a different place because they've moved the boat overnight. There's some sort of crisis going on. So the picture on the right there is just me one morning. I woke up, I hadn't had my coffee. I was the shipboard scientist, so all the problems came to me. And one morning there was a puffin in the head. So my first order of business was, okay, let's deal with the puffin. So I grabbed a towel and had to get this little puffin and get it overboard. So it's a really fun type of field work, and it's challenging, but it's kind of a neat and rare experience. So okay, so that's where we are. We're very remote. And I want to talk a bit about this chain of islands and why it's there. So this is what we refer to as the Alaska Aleutian subduction zone. And a subduction zone is one of the main ways we get volcanic activity on planet Earth. So all of the chains of islands that you see rimming the Pacific are subduction zone volcanoes. They're the most explosive, the most hazardous. They produce the largest volcanoes on Earth. These are different from places like Hawaii or Iceland, which are driven by mantle plumes. And the way this works in subduction zones is basically the way we've got it diagrammed here in this lower figure. Basically, we have one of the Earth's tectonic plates, in this case, the Pacific plate. It's getting forced underneath another tectonic plate, the North American plate here. And this plate that gets subducted or forced down is very full of water, other volatile elements. It's got its own chemistry, and that water gets carried down in the rocks, buried into the rocks and locked into their chemical structure until that plate reaches a certain depth. And then under pressure and temperature conditions at great depth, that water starts to come out. And as it comes out, it starts to heat up this little core of mantle that gets trapped in the wedge of the two subducting plates and causes it to melt. And from that reaction, then we start to get this upward system of lenses of magma that ultimately erupt and carry a lot of that water with it. So that's why these are some of the most explosive. They have a lot of water and other gases in them compared to places like Hawaii and Iceland. So that's subduction. This is a well-known, well-characterized subduction system with many active volcanoes. All right, so the Islands of the Fort Mountains is a place I've mentioned, the location of our caldera, and a place you probably haven't heard of. And so I'll talk a little bit about what it's like and why we were interested, and why we're interested in general in eruptions that happen in such a remote place. So the Islands of the Four Mountains is actually more than four mountains. We're not entirely sure where the name came from. It's an old name from early mariners who traveled in the area. And what I'm actually going to be talking about is the eastern set of the Islands of the Four Mountains. So these that are shown in this really nice picture up on the top. And so we're looking to the southwest here. You can see in the little schematic an arrow that shows you the look angle. And the first thing I'll point out, and the hindsight obvious clue, is that the islands in this part of the Aleutian arc form this semi-ring-like structure. So that was something that, as my colleague and I were sailing into the islands in 2015, we were standing on the bow of our boat. We were looking at these, and my colleague turned to me and said, "I've always wondered why there's this collection of little islands here. It's very different from the neighboring volcanoes, which are one big landmass and one big summit and vent." So that, in hindsight, turned out to be the first clue. So the islands I'm going to focus on are called Uliaga, Cagamil, Tanna, Cleveland, Herbert, and Carlisle. Cleveland was really our target of interest, and I'll talk a bit about Cleveland in the next few slides. But we also visited a few of these other islands, although we really were only focused on Cleveland during this study. And it turned out that, the islands as a collection really told a much more interesting story. So just to talk a bit about Cleveland, Cleveland is actually the most active volcano in North America. It has, on average, 1 to 2 explosive eruptions every year that we know of, at least going back to about 2001 and probably earlier than that. And these aren't huge eruptions. I'll talk in a sec about why they're important. They're not, Mount St. Helens style or size. They're much smaller than that. They tend to be fairly quick. They put out these beautiful puffs of ash, these ash plumes, and this is actually a great photo taken from the International Space Station that happened to be passing overhead right in 2006 during one of these. So you can see this nice ash cloud that's coming off of the vent of Cleveland. But it does occasionally have larger eruptions. So we know of larger eruptions in 1944 and in 2001. And again, those aren't, as large as something like a Mount St. Helens, but they're a bit of a bigger scale. But this is typical activity, are these small, short puffs, maybe a few hours long at a time. So why do we care about a volcano that's so isolated and where very few people live? And that's basically because of the figure in the lower left here, which is showing you air traffic routes. So the Aleutian Islands, and actually also the volcanoes here along the Kamchatka Peninsula and the Kurils in northern Japan, are below some of the most heavily trafficked air corridors on Earth. So this is an air corridor called the NOPAC, the Northern Pacific Air Corridor. And it's heavily trafficked because if you take a flight from anywhere on the eastern seaboard, Washington, D.C. or Baltimore or New York, Chicago, Boston, to anywhere in Asia, Beijing, Tokyo, you're going to take a great circle route that takes you very high altitude. It's actually the shortest distance on a circle, and you fly directly over all of these volcanoes. And the punchline here is that volcanic ash, which is actually not ash, it's little tiny shards of glass, does not play very well with jet engines. And there have been rare incidents where a jet has encountered one of these ash plumes and ingested some of that ash into the engines and had engine trouble. So because of that, many of the world's volcanoes that are quite remote are still heavily monitored so that a warning can be given out through, for example, the Federal Aviation Administration to pilots to do a quick reroute. And so this works really well. And if you were on one of these flights that got diverted, you probably wouldn't even know it because it happens very frequently. But there's basically a 24/7 watch office whose job it is to, when an eruption occurs, make sure that information gets disseminated so that we can avoid these encounters, and especially in an area like the Aleutians. So we can tell, even if we can't tell beforehand that the eruption was going to happen, we can still detect the ash in the atmosphere with satellites. But ideally, what we want is to have a little bit of warning before that ash cloud gets released. So many of these volcanoes have continuous monitoring, mostly through seismometers, which are very reliable in picking up small changes in seismicity before an eruption. There are a lot of seismometers on the volcanoes throughout the Aleutians, but at Cleveland, there are only 2 seismometers, and they've only been there since 2014, largely because it's a really, really inaccessible place. So there are a few other instruments out there, but mostly just a couple seismometers, and they do a pretty good job. So one of our goals was actually to see if we could record one of these explosions and see what we could see in our seismic data that might help to give this warning. So on the right here, you're just seeing some fun shots that we took from our helicopter during 2015 of a different type of volcanic eruption that also happens at Cleveland in between these explosions, called a dome building event. So we actually affectionately referred to this as the Oreo cookie, because obviously it looks like one, but this is actually just a little dome of magma that got squirted out like toothpaste. And what it does is it plugs up the vent, and that allows some of that gas to accumulate, and then we get an explosion. So we often see these cycles of going between one of these domes, and you can see it's quite hot. These are our thermal images on the top to one of these explosive events. So very active. Like I said, we think it's been the most active volcano in North America. Somebody said it looks like a sea urchin. Actually, now that you point that out, I agree. We think it's been the most active in North America since 2001, but we don't have great records going back since these aren't huge eruptions. We do have some evidence, however, that it's actually been doing what it's now doing for decades and possibly even longer. So we have a few photos here that show on the top, maybe more of a gas plume, but maybe containing a little ash in the 30s. some melting at the summit in the 60s, showing maybe the presence of one of these domes or some sort of heat. Another little ash plume coming out. So it's very, very continuously active. And one of my questions when I first went out there, well, what's so special about this volcano compared to its neighbors that makes it so much more active? And I'll get to that. So the last eruption was in 2020. And so we're probably due for one pretty soon. Okay. So as I mentioned, we did not go out there looking for a big caldera system or a big volcanic system. What we wanted to do was simply for a year put out more seismometers to see if we could do a better job with precursors. We were hoping to record an explosion, and we did with our seismometers. And also we really wanted to see if we could get a sense of where the magma was, both in depth and relative to this vent. And I'll get to that in a sec. We actually did a pretty good job of that. So what we did in 2015 was augment the 2 stations that went out with 12 additional stations. These are these yellow triangles here and white triangles. This is what they look like on the top. Basically, we dig a hole in the ground to put our sensor in. We love the Home Depot buckets. We use them to kind of cap the seismometer to keep it dry and a little clean. And then we have some electronics on the surface that record the signal and give it power and so on. So this is kind of what it looks like. Like I said, we do a lot of digging. My job is basically to dig holes. And then this is just a picture of the 2 permanent sites. One of them, they're a little beefier just because they're meant to stay out there for years and years. So this is a site that's maintained by the United States Geological Survey, Alaska Volcano Observatory. So that's what that looks like. And there are a couple there, these 2 black triangles, CLES and CLCO. So those were our goals. And we were very lucky. You can never count on this when you put out instruments, but so we put out 12 seismometers, and we recorded actually quite a bit of seismicity. You can see it up on the top here. These blue circles are all individual seismic events, which is not surprising for an active volcano. Most of them are beneath the vent. So this big cluster right here in the middle of our sensors, but one surprise and one first clue were these guys off to the side. Those were unexpected. So that puzzled us a little bit, but we moved on. I'm gonna go ahead and skip that. Now, another thing that we did while we were out there was measure gas. And so volcanoes typically put out quite a bit of SO2, sulfur dioxide, stinky stuff, and CO2. And that tells us a little bit about where the magma is coming from in depth. Usually the more SO2 and CO2, the deeper it is. And so what we do is we decided to duct tape the sensor onto the helicopter. You can see my colleagues Taryn and Cindy there duct taping it on. We flew it around basically anytime we were in the helicopter. We happened to pass over some what we call fumaroles or gas vents on this old volcano Tana, which we thought was extremely old and possibly extinct. And one big surprise was that actually we found quite a lot of gas coming out of these vents, and the gas actually told us that this was fresh, deep magma that was underlying this big old volcano that we did not think had anything going on. So that was surprise number 2. All right. So at this point, we were starting to think big, and we thought, okay, well, let's go back to the question. Why is there this little cluster of islands here so unusual? And furthermore, why is it in a ring? So the idea that came up to explain this and all of our anomalous observations so far was that what we were actually looking at Cleveland was the edge of what we call a caldera. So caldera is a type of volcanic feature. It's basically, we refer to it as a caldera, the depression that's formed in the Earth's surface when a large body of magma, so you can see this diagrammed below, gets drained through a major eruption, and the roof basically collapses in. So we get this circular collapse feature. And there's a lot of detail on here. I mostly want you to just see the circular collapse feature. We often then start to see vents starting to form where magma leaks up around that ring of that caved in roof. So this is possibly what we thought we would be seeing. And then the other thing I want to mention here is this deposit in yellow, which is called an ignimbrite. And that's a very typical deposit from a massive eruption very close to the vent. So we started throwing this idea around. And as we started doing that, we started thinking about, okay, the Aleutians actually has a lot of calderas, and you can see them in red circles here. Some of them are quite large, and in fact, the largest ones in the Aleutians are actually in the vicinity of the IFM. So the IFM is here, and in fact, it's a gap in some of the location of the biggest calderas. And so I just want to mention an aside for those of you that are interested in history. Again, these are very remote, but we've started to learn about their impacts and how those impacts can be global. And so just as an example, the caldera-forming eruption of the volcano just to the east of the IFM, which is called Okmok, in 43 BCE, was actually recently linked in a paper last year to the fall of the Roman Republic. So basically the amount of ash that came out during this eruption was voluminous enough and traveled far enough that it disrupted climate globally, leading to various impacts on societies as far away as Europe. And so this argument has been that actually one of these neighboring calderas has resulted in massive socio-political upheaval. So this is why we're interested in these. They tend to have global effects. So the next thing that happened was we started talking with another group that had been working out in the islands of the Four Mountains. They were actually out there doing an archaeological study to look at early patterns of human migration. And so they were actually just using ash deposits and dating them just to get time constraints on artifacts they were finding. And they happened to stumble across a very unusual deposit that they quickly recognized was an ignimbrite. So this was something that nobody had observed before. We found it outcropping in a couple of places on Tanna. So this is Cleveland, our active one. But we found these very large deposits that are very consistent with a massive eruption in this area sometime in history. So this was clue number 2. So we started to get really excited at this point about our caldera idea. We then started to realize that in addition to these gas vents or fumaroles that seem to have a magmatic composition, there were several other places in this old eroded other islands that had very strong thermal features, again, suggesting that maybe the volcanic activity currently, or the magma underlying this area, was much more distributed than just under Cleveland. So as an example, on Cagamil here in D, we found that there was a large area of degassing. We haven't been able to sample it, so we don't know much about it. But again, this is starting to tell us about something that's got a much wider scale than what we previously thought was the active volcanism in the islands of the Four Mountains. So of course, nothing is easy. So the challenge then is, well, we want to see, okay, so we see these this ring of islands that might be these post-caldera vents creeping out that might be telling us about the edge of a caldera, but obviously the biggest confirmation would be to see this big circular depression. And of course, the challenge here is that's, if it's there, hiding underwater. And so this is a much more challenging environment. You know, it's very easy to recognize a caldera when it's exposed above water. You saw the one in the photo of Okmok, it's pretty obvious. But when they're underwater, you know, we're really limited as to what we can do. And we weren't able to get back out there to actually do submarine work. So we had to get really creative. And we kind of talked about, like, let's start just digging under the sofa cushions to see, you know, what we can find, if anything. So the first thing we did was try to get the best bathymetry to see if we could find some evidence for a big depression in the center of the ring of islands. And it turns out that the best thing we could find were some depth soundings that were taken throughout the islands of the Four Mountains in the 1950s by NOAA. So this was an effort after World War II to try to map the bathymetry throughout the Aleutians, partly for submarine operations, partly for fishing. And they're actually pretty good data. So we reprocessed them. This is the original chart here. And we've digitized and reprocessed them into this bathymetrics. So what you're looking at now is basically the color codes are telling you the elevation of the sea, the floor underneath the sea. And what we started to see were actually some structures that looked like they might outline the rim of a caldera. In particular, this the shoal here and this ridge here, and then several depressions in the center. So the surface of the seafloor inside and just around the ring of the islands is actually pretty consistent with what we see from places where we've actually been able to go and take a remote sub, and do this mapping properly. So we were very encouraged, and it's poor resolution data, but it is very suggestive of a structure that looks like what we might expect for an old caldera system inside this ring of islands. And then the final piece of evidence was actually the most amazing long shot that worked out. We decided to look at gravity, and gravity, if we were able to say something about the gravity in this area, it would tell us about whether there was potentially some magma still left underground. So people talk about gravity on Earth being 9.8 meters per second squared. That's what we all learned, but that's just an average. So gravity on Earth is actually variable from point to point. It's a function of topography. So the farther you are in altitude, the farther away you are from the center of mass in the Earth, so you feel less gravity, but also that topography contributes to gravity because it's mass. So we have to actually separate that out before we can see what the gravity is below. And typically when we see pockets of molten magma, they produce a gravity low. They're less dense than the surrounding rock. So this work is usually done with instruments that you place out on the ground, and you very carefully measure the displacement of a mass on a spring. But what we were able to do, because we couldn't get back out there, was use what's called satellite gravity, satellite altimetry derived gravity. So there were several satellites orbiting the entire planet that actually mapped the shape of the ocean surface. So again, you would think it's liquid, so it should be flat. In fact, no. The gravity of the rocks beneath the ocean actually deflects the water. So the water surface along the seas is actually a bit bumpy in a way that reflects the solid that's beneath it. And so by some very careful processing, we were actually able to figure out that there was a 25 milligal gravity low centered inside our ring of islands. And so by further modeling, we were looking at basically the gradient of this change, and we see some more out here that might suggest, again, something additional outside the ring. We can actually say that it's within the crust. It's not a surface collection of sediment with lower density. It's actually something that's down at the position where we might expect a magma chamber. So this was our final piece of evidence and really the nail in the coffin for this story. So we were very excited about that. So together, all of these pieces of evidence pretty much line up to our new hypothesis that there's a caldera system. And of course, the question then becomes, well, how big is it? So this is a more challenging question to answer. And so we're just doing a ballpark here. Obviously, we see more complex structure than a simple ring. But if we just take as a first order estimate, the radius of this, or the diameter of this ring of islands, we see that if these were the edge, if this was delineating the edge of the caldera, it would be 25 by 20 kilometers. And that would actually make it the biggest caldera in the Aleutian arc. We think it's actually potentially a bit bigger, but this is our conservative estimate. So just by comparison, Okmok, which is the one that messed up the Roman Republic, is only 10 by 12 kilometers. So this is twice as large potentially, and potentially larger. So we think it's quite big. We don't know how big. This is maybe a first estimate that we hope to refine. But we do think this is a fairly large system, and among the, if not the largest in the Aleutian arc. So quite exciting. And of course, we're now very interested in trying to figure out when this structure formed. When did this massive eruption occur here? And did it have impacts on the climate or society or the megafauna or so on? Those are questions we really can't answer until we're able to get back there. So I want to wrap up by bringing up the term supervolcano. So we presented these results at the American Geophysical Union conference in this past December for the first time. And we got a lot of positive reaction from our colleagues in volcanology. And we also got a lot of news coverage. And it was quite fun to watch the news coverage. We had some really great coverage in National Geographic. They always do a fantastic job. But we expected, and of course it happened, the term supervolcano. So you see here, geologists think they found Alaska's Yellowstone. And a rebuttal from somebody in the science community who writes popular science articles saying, no, we haven't. And the reason is that, Yellowstone is often talked about as a supervolcano. And we don't like the term supervolcano because it implies that that system, that supervolcano, can only have massive eruptions. And that's in fact not true. Even at the Earth's largest calderas, including Yellowstone, most of the eruptions are very, very small. In fact, the next eruption of Yellowstone is likely to be very, very small. So we don't think of any volcano as a supervolcano. We just think of them as some volcanoes have the potential for super eruptions, but that doesn't mean that their other eruptions at later or earlier points will be large. In fact, they're likely to be small. And if you want to hear a very eloquent take on this, you can look up this nice article, Why I Dislike the Term Supervolcano, which was written by the Yellowstone Volcano Observatory scientist in charge, a friend and colleague of mine, which talks about this point and our understanding of these big systems. So in truth, this actually helps us explain why Cleveland has these frequent small eruptions, because this is what many caldera systems on Earth do. So we don't think this system is as big as Yellowstone. We think it's actually more analogous to some place like Sakurajima in Japan, on the island of Kyushu in southern Japan, which is on the rim of the Ira caldera. So a large, older caldera, but its active vent, Sakurajima, has very small but very frequent explosions, in fact, several per day. And this is very typical of vents that sit on the rim of old calderas. And so it helps us explain why Cleveland is always active, and it helps us maybe anticipate more about what Cleveland will do in the future. It's probably likely to continue doing what it does because it's basically feeding off, it's got a pathway now that's unobstructed, and it's basically bleeding off residual gas and heat from this old big magma chamber that partially evacuated during the caldera. So this is kind of a nice insight for us for hazard assessment and what we expect this volcano to do going forward. So just to summarize, we have multiple lines of evidence now suggesting the presence of a very large caldera in the islands of the Four Mountains. We think it's perhaps the largest caldera that's been identified to date in the Aleutian Arc. We still don't have constraints on its age. We have some guesses. We don't know its exact size. We don't know its structure fully, where the walls are, whether there are multiple blocks that were down dropped, and even whether we're right. I mean, there's always a chance that we're misreading some coincidental clues. So right now, our hope is very much to return to the IFM for detailed follow-up work. And we have a proposal currently in review at the National Science Foundation to return with basically every tool we can get our hands on to do detailed mapping and additional instrument guided work in 2022 through 2025. So I guess I would just say stay tuned. And at this point, that's everything I've got. And I think I've got about 10 minutes left for questions. Like I said, I'm happy to talk about this study or about volcanoes in general. Okay. So I see the first question from Jennifer. What do you think about the fun going on at Reykjanes, and where do you stand on whether that's just going to keep spewing lava for a few decades? I'm actually getting on a plane to Iceland in a few hours to take a few instruments to Reykjanes. I think it's a brilliant eruption because it's not very hazardous. It's a really great tourist volcano. It's not in a populated area, but it's just a beautiful eruption to go and see and do science experiments, collect data. Right now, the thinking is that actually this eruption is likely to herald a fairly long-term period of eruption on the Reykjanes Peninsula, and that's consistent with what's occurred in the past. So we haven't seen an eruption on the Reykjanes Peninsula for about 800 years. But in the past, in the geologic record, when it gets active, it stays active for decades to potentially centuries. And that may not be at the current vent. It may move around a little bit. We've seen seismicity throughout the peninsula, and in fact, it's moving around a bit. It'll probably be very similar activity to what's going on now. So really beautiful and fun. So I'm very excited to go this weekend. And I hope if you get a chance to visit, or at least to watch the live cams, which have been great, you check that out, because it's been one that we're all excited about. Okay, so I see a question also from Jennifer. Follow-up. I kind of hope it does keep spewing. Iceland could use the money. Yeah, Iceland is a very tourist-dependent economy, and they're thrilled, and they've actually been really amazing. One of the things I've appreciated is how they've worked very hard with civil protection to make this accessible to tourists. So early on, people were going out at night. You know, it's a bit of a hike. You know, the flashlights were dying, they didn't have cell, they were getting lost. And so now they've got a great system where the path is illuminated, you sign in, it's very safe. There are people out there who are from civil protection. And I think it's just amazing to make that, you know, make sure that people who want to go see can go see. And I hope it keeps continuing, because it's, you know, it is, I know you're saying sarcastically, and I'm not saying either sarcastically. It's one of those ones that we appreciate, because it's not particularly hazardous. It's great for science, and it's great for people who just want to go see an amazing natural wonder. It is one of those ones that we don't stress about. It's a fun one. Okay, Terry?
Dr. Roman, we
Yes.
also had a question from Henry Meyer. The monitoring station, yes, I am speaking the English very goodly. The monitoring stations you installed, how long will they last?
Yeah, so the ones we put out are 12. Were only designed to last a year. We had them on batteries, huge banks of batteries that would power them for about a year. So that's typically when I do an experiment. That's about how long I aim for, and sometimes I'll go in and swap the batteries for another year. The stations that the Alaska Volcano Observatory runs are permanent. They're expected to last indefinitely, and they go out every year or so to make sure that, you know, everything is working and the radio link is correct, and so on. So we want them to last as long as we can, but realistically, for my sort of experimental seismology, we aim for about a year. I see a question from Jerry in the Q&A. Could the caldera have lava tubes that are now underwater? Yes, and one of the things we're really interested in looking at is whether there are any vents in that depression. So often we see gas vents or maybe old structures like lava tubes. And so one of our proposal elements is actually to take out a ship that can do some really high resolution imaging, even tell us where there are maybe streams of gas bubbles coming out, so we can see, you know, are there pockets of lava or pockets of magma? Are there structures like lava tubes or small domes on the surface? So yes. Another question from Henry: how useful are the satellite views? They are very useful to us, and in particular for volcanoes that don't have any ground-based instruments. Agencies like ABO rely entirely on satellites, and they do multiple daily checks of different satellites that look for thermal anomalies, that look for gas anomalies, that look for ash anomalies to just see the ash plume. And a lot of these are semi-automated, but they get checked by an analyst. We also have satellites that can tell us about deformation, which is amazing. Obviously, when you do it from a satellite, you have to have a bigger signal. So it's you know, we can see more detailed processes with instruments on the ground. But in the past decade or two, volcanology has really embraced satellite remote sensing, and it's been a huge boon, especially for remote volcanoes like this. And in fact, in Nyiragongo, just in the past few days, a lot of what we've seen is from satellite imagery. So we're always rooting for new sensors to go up, and they're always getting better. And like I said, the gravity was one we didn't know if it would work. Can we do gravity from satellite? And it turns out we can. So I don't see any other questions unless I'm missing some. Somebody said, so big you didn't see it right away. It's, you know, we're laughing because it's just so obvious in hindsight. And my closest collaborator, the guy who said, what about all these islands? You know, he explained this to his teenage boys, and they said, duh, Dad, how did you miss this? But it's really true that we were so zoomed in on this one volcano that, you know, we missed the bigger picture. And this is kind of, again, what I mean about, you know, until we had some clues that led us to it. Yeah, and in hindsight, it just seems like, oh, how did we miss this? Yeah. But this is what we do. We have to go out to do a problem. We're very focused. We're very fast. We're constrained with where we can put things, and we always need to step back and look at the bigger picture and hope that something we see leads us in that direction. I think that's the big lesson. How deep is the deepest point of the caldera? It's quite shallow. It's about 200 meters. So it's actually a bit of a challenge for us getting some of the big fancy boats in there with big tools because they can't go into shallow water. So we know that it's quite shallow there, and there's a lot of fishing there that's done additional depth sounding work. So we do have a pretty good sense of the general depth, but it's, again, typical for what we see in a caldera of several hundred meters offset when you take the top of even the general top of the seafloor, the top of the vents to the bottom of the caldera. All right. Let's see. And
so,
and
Dr.
yes,
Roman.
robots.
Yeah, I'm sorry. Yes, there was another question.
Yeah, we have some colleagues who are interested in bringing out some experimental robots to take a look. But our aim is to use the known tools, which are basically sensors that we mount on the base of the ship, and we ping things to the surface. But yeah, it's a great place for ROVs.
Okay.
Well, thank you, everyone.
To wrap up with the typical 2-minute warning, do you have any personal website, contact information, organization that you'd like to show?
I don't have it to show, but if you go to my website is Diana C, as in Charlie, Diana Christine Roman. So dianacroman.com. You can see more about my research and find my contact information and some other talks I've given. So please have a look if you're interested. And thanks for your attention and for the great questions.